Elon Musk and his team behind the Neuralink brain implant have just provided us with the latest update on their first human trial, with the promise that a second human patient is coming very soon using an upgraded Neuralink device. Progress so far has been a mixed bag of unprecedented success and unexpected setbacks, all of which is helping to propel the company forwards to their ultimate goal of unlocking superhuman capabilities. This is everything you need to know about Neuralink right now. Elon Musk is now promising that the second human Neuralink operation will be moving forward within the next 2 weeks. This is a slight delay from what we had been expecting, which was to see patient number 2 completed in June. We've learned that a Neuralink surgery was originally scheduled to go forward on June 24th at the Barrow Neurological Institute, but was cancelled after the patient candidate had to withdraw from the test. Barrow CEO Michael Lawton has said that the withdrawal was due to health concerns with the patient, and he notes that these concerns are unrelated to the brain implant procedure. Elon and his team have also revealed that Neuralink's second human implant will not be like the first. Neuralink's first human patient, Nolan Arbaugh, underwent his brain implant surgery in late January 2024. This procedure was successful and Nolan didn't experience any negative side effects from either the surgery or the implant. For the first couple of weeks, Neuralink's N1 brain-computer interface performed flawlessly, allowing the user to interface with their computer mouse just by thinking about the movement. This immediately gave Nolan the ability to surf the web and play games independently and without the use of a mouthstick for the first time since he was paralyzed in a diving accident 8 years ago. During weekdays, Nolan spends up to 8 hours a day contributing to Neuralink research. On weekends, his personal and recreational use of the implant can exceed up to 10 hours per day. He's been able to reach up to 69 hours per week of brain-computer interface with the N1 chip. Neuralink engineers confirmed that the current device has a battery life of 4 to 5 hours and a charging time of about 45 minutes. They said that Nolan has been keeping an inductive charging coil tucked underneath the beanie that he's often seen wearing, so that he can quickly and independently recharge his device. Neuralink also says that Nolan is already moving his computer cursor at speeds beyond the ability of a person using a mouse, something Nolan has been demonstrating often with his live streams on the X platform. The standard for measuring speed and accuracy of cursor control is bits per second or BPS. And that's what Neuralink is calculating during these grid tests where you see the cursor moving around and clicking on different boxes. On day 1, Nolan set a new world record of 4.6 BPS. 3 months later, Nolan was already achieving 8 BPS and is currently operating at a rate of 9.5 BPS, double his previous record. The Neuralink telepathy software is able to distinguish between left and right clicks and allows for movement of the cursor that is precise enough to click on the smallest icons and buttons of a laptop screen. However, this initial trial has not been without issues. What we know is that in the weeks following the surgery, a number of the electrode threads that were implanted into Nolan's brain tissue started to retract, essentially cutting off some of the communication between the brain and the implant. During the surgical procedure, Neuralink's R1 robot was used to insert 64 threads into the outer layer of the brain, the cerebral cortex, and specifically, this is targeted into the motor cortex region of the brain, penetrating just a few millimeters deep into the tissue. Each thread is thinner than a human hair and carries 16 electrode sensors, giving the Link device a total of over 1,000 connection points into the neural network of Nolan's brain. From here, the electrodes can detect bioelectric pulses created by neuron activation within the cortex layer. The Link device uses signals collected by the threads to create a digital representation of the brain activity that can then be transmitted via Bluetooth into a nearby computer device. Neuralink has confirmed that only 15% of the Link electrodes remain in place today, but according to Neuralink, these remaining threads have stabilized and improvements made to the software algorithms that decode his brain signals have restored Nolan's brain-computer interface capabilities. So when the threads retracted from the brain, that decreased the number of electrode interfaces between the Link implant and the motor cortex. Neuralink has confirmed that there are 2 contributing factors to the thread retraction. One is an air pocket that is created between the brain and the skull. Neuralink says this is common during brain surgery and it's typical for the surgeon to introduce a small amount of air into the skull. The reason they do that is to create more room. By lowering the CO2 concentration in a specific area, they cause the brain to shrink a little bit and pull away from the skull, providing more room to work. The downside is that once inside the skull, that air pocket can now migrate. And Neuralink believes that the air pocket moved from the front of the brain to underneath their implant site, which pushed the brain away from the implant and tightened the threads. In their next operation, Neuralink plans to maintain a normal CO2 concentration, or even slightly elevated levels, which will allow the brain to keep its normal size and shape during surgery, which should eliminate the air pocket. They also believe that by moderately resculpting the surface of the skull, they can get the implant to sit closer to the brain and reduce the gap underneath. The second factor is brain movement. Neuralink was not anticipating how much a human brain would move compared to a smaller animal brain. They found that the surface of the brain actually travels about 3 millimeters even when the person is just sitting still and breathing. So that makes targeting with the surgical robot very difficult. One solution here is more precise targeting on the surface of the brain. The outer layer of a human brain has a very complex structure of folded layers. This increased surface area is what gives us our intelligence, but it also presents a challenging landscape for inserting the Neuralink electrodes. For their next procedure, Neuralink will be targeting only the high points of the surface and avoiding anywhere too close to one of the folds. This will provide better connectivity to the neuron layers, and it will make sure the thread is anchored in the brain tissue. Another solution is simply to go deeper with the thread insertion. Essentially, Neuralink will be broadening the range of thread depth with their second human operation, now that they know retraction is a possibility. So the threads will be placed at depths ranging from 4 mm to 7.2 mm. Neuralink engineers believe that as long as the threads can stay planted long enough for the brain tissue to begin healing over and regenerating from the surgery, then they should remain anchored and stable for the long term. It's also important to note that Neuralink is the first brain implant with the ability to have varied electrode depths. Previously, we've only used these hard spiked arrays with pins that are all the same length. What's interesting here is that Elon says the updated Neuralink Gen 2 implant will have fewer electrodes per thread, going from 16 down to 8, and that's because the company now has a higher confidence in the thread's ability to reach neurons, so less electrodes are needed. He believes that Neuralink can achieve double their current bandwidth just by getting more accurate with the thread placement. One of the engineers pointed out that they can also move to a higher thread count to increase the number of information channels to the brain, potentially reaching up to 3,000 channels. Their current device has a maximum of 1024. Elon and his team are highly confident it won't be long until a Neuralink user can communicate much faster than any average human being, not just through a computer. But Elon is already talking about this idea of being able to instantly transmit a concept or idea using digital telepathy without even any need for words or language. He's also highly confident that Neuralink will be offering their first solution to blindness in the near future. His team said that there's already been several animal trials with stimulating the visual cortex of the brain. It's still very basic stuff. They can essentially light up a pixel in the vision of a monkey, then by having the monkey look toward the light, they start to get an idea of which neurons are connected to the various pixels that make up our vision. So the first iteration of Neuralink's blind sight will be very low resolution, equivalent to something like an old Atari video game. But it will improve over time. One other Neuralink capability that was teased during the update was an interface with Tesla's humanoid robot, also known as Optimus. The team believes that a paralyzed individual should be able to use their Neuralink to control the movement of the humanoid robot. That can range from manipulating a robotic arm to help them move objects, or scratch and itch, all the way to remote controlling a full robot body. In a slightly more practical application, Elon thinks that they can have Neuralink users steering their own electric wheelchairs using Bluetooth communication from the implant, which would be a massive upgrade for the independence and mobility of a paralyzed individual. It was also confirmed that unlocking the full capability of Neuralink is going to require multiple device implants. We have this ex-post from Elon Musk where he writes, "Nolan and I discussed a possible second Neuralink that would allow his other brain hemisphere to interact telepathically with his computer. This would be like having two-handed control ability, the equivalent of mouse and keyboard." The idea here is that a Neuralink on the left side of your brain will interface with the right side of the body, such as using a computer mouse. But to get the equivalent functionality of using both arms at the same time, you need implants on both hemispheres of the brain. Nolan was recently on an episode of the Joe Rogan Experience podcast, one of many interviews and conversations that he's done with the media since his identity was revealed in March 2024. While on Rogan's podcast, Nolan talked about his experience playing video games with the Neuralink device. Nolan said, "I basically have an aimbot in my head. They'll probably have different leagues for people like me because it's just not fair." Nolan went on to explain that his digital telepathy is faster and more accurate than playing with hands and a controller. This is a bit of foreshadowing towards Elon Musk's end goal with Neuralink. He believes that this device will allow people, all people not just those with disabilities, to interface with technology at a significantly higher bandwidth than a mouse and keyboard or touchscreen could ever possibly allow, essentially knocking down a barrier between the human brain and the computer, bringing us much closer to a cybernetic superhuman kind of ability. Now, that all could be great, but it can also create a whole lot of new problems for security and privacy. This is also something that Nolan touched on in his talk with Joe, saying, "I mean, people ask me all the time if this thing can be hacked, and the short answer is, yes." This is easily one of the most frequent points raised in the comment section, so here's the closest thing we've had to an answer. Nolan went on to say, "But at this point at least hacking this wouldn't really do much. You might be able to control my cursor on my screen and make me look at weird stuff." So basically saying that the danger of Neuralink will scale with the capabilities of Neuralink. For now, it can't do very much. The functionality is limited, meaning that the risk is likewise pretty limited. It all depends on where we go from here.